So in this problem, we're asked to find how the drag force on a moving ball depends on its velocity, its radius, and the density of the surrounding fluid. And this is actually going to be one of those few physics problems in which you don't have to draw a picture, because this isn't really a physical situation. We're only comparing these mathematical quantities, so it's almost entirely a mathematical process. So first, we're given that force depends upon these three quantities: V, rho, and r. And each of them are going to have to be raised to some constant power, alpha, beta, or gamma. And this is what we're going to try to find. We're going to try to find how force depends upon each of these to what power. And so, immediately what you should be thinking is that if force truly only depends on these three things, then the dimensions have to work out. Force has to have the same dimensions as velocity to the alpha, density to the beta, times radius to the gamma. And so what we're going to do right away is we're going to write down what those dimensions are. So first of all, force has dimensions of mass times length times time to the -2. And if you have trouble remembering things like this, especially for the more complicated things like force, or later we're going to be learning about things like energy, you can remember your formulas. So for instance, force equals mass times acceleration. If you can't remember the dimensions of force, you can go to that formula and think, okay, mass obviously has dimensions of mass, and I think we can all remember that acceleration has dimensions of length per time squared. And then you can put that together to remember what the dimensions of force are. And now for the other three, we have velocity equals dimensions of length per time, density as dimensions of mass per length cubed, or mass per volume, and radius just has dimensions of length. And so now what we're going to do is we're going to take this equation, and we're going to take these dimensions, and we're going to make sure that they all work out. So the dimensions of force, m, l, t to the -2, have to equal l, t to the -1 raised to the alpha, times mass per volume raised to the beta, times length raised to the gamma. And now we're going to group these terms a little bit more intelligently so that we can compare the powers from the left side to the right side. So first we're going to take mass to the beta, length to the alpha plus gamma minus 3 beta, and then time to the minus alpha. And right away, this is going to give us three equations just by comparing the powers of each term and making sure they're the same. So we're going to be given beta equals 1 from the mass term, alpha plus gamma minus 3 beta equals 1 from the length term, and minus alpha equals minus 2 from the time term. And we can solve this pretty easily. We're going to get alpha equals 2 right there, beta equals 1 right there, and then gamma equals 1 plus 3 from the beta term minus 2 from the alpha term, which is going to equal 2. And so then we can just look at these and go back to that formula right there, and we get force is proportional to velocity squared times density times radius squared. And so what this means is that if the velocity of the ball is doubled, or the radius of the ball is doubled, then the drag force is going to be quadrupled. But if the density of the surrounding fluid is doubled, the force is only going to double.